This video describes the EveCore architecture. EveCore is a modern 8-bit microcontroller design. This video describes the instruction set architecture of the EveCore, which includes the registers and all the instructions. There are actually two videos. One is shorter and more concise, while the other is longer and goes into more detail. You're watching the second video that's longer. The first video is targeted at someone who has a good background in computer architecture and some assembly language programming experience. The video you're watching is targeted at someone who is perhaps learning about computer architecture and maybe hasn't had as much assembly language programming experience. This video is part of a series on how to design a core, and in other videos we walk through the Verilog implementation of a core. In particular, we'll be targeting the FPGA board that is called the NAND Go board. This has a pretty small FPGA on it, but the information that we'll go over in this series can be targeted to any FPGA. Okay, with that said, let's go ahead and get started. This diagram shows the overall architecture of the EveCore. To describe any instruction set architecture, we need to talk about both registers and memory. On the left we have the registers, and on the right we have the memory. Most of the registers are 8 bits in length, and you can see the least significant bit is 0, and the most significant bit is number 7. There are 8 8-bit registers, and they are named A, B, C, D, X, Y, M1, and M2. A is the workhorse register, also called the accumulator register. Now the X and Y register can be combined into a 16-bit register, and that register is called XY. And likewise, M1 and M2 can be worked on together as a single 16-bit register, and that register is called the M register. In addition, we have a program counter, or PC, and that's 16 bits, as you can see. And we have a stack pointer register, again, also 16 bits. The memory is divided into two separate sections. We have a flash memory. That's where the program will live, and that is a read-only memory. It doesn't change during execution. And then we have a RAM memory, and that's where any changing data is stored. The architecture will accommodate up to 64K bytes of flash memory and up to 64K bytes of RAM memory. So in order to access 64 kilobytes, we need 16-bit addresses, and that's why the program counter is 16 bits and the stack pointer is 16 bits. The program counter will index into the program memory, and the program memory is addressed from location 0 at the so-called bottom of memory, or the beginning of memory, all the way up to a number with 16 1-bits, which is FFFF in hex. The stack pointer will index into the RAM, and again it's 16 bits, and the RAM is addressed from starting memory at address 0000 all the way up to an address of all ones of 16 1-bits, that is hex FFFF. In addition to the registers that we've talked about so far, we also have 4 individual bits called the condition code bits. Sometimes these bits are called the condition flag bits. The first one is the carry bit, or the carry flag, and then we have the 0 flag, and then we have the sign flag, and then finally we have the overflow flag. These bits will be set by certain instructions, in particular the arithmetic instructions and the compare instructions, and they will reflect the outcome of the operation. For example, if the outcome is all zeros, the 0 flag would be set to 1. And then later, the program can test these bits with some of the conditional branch instructions. So for example, we can compare two values, and then the conditional branch instruction will test various bits in the condition codes to determine whether it was, say, less than or whatever, and take a branch accordingly. So next, let's move on to talking about the instructions. This architecture has about 155 different instructions, although after building an FPGA, you can choose to add more instructions if you want. The instructions are between 1 and 3 bytes in length. The first byte is always an opcode byte, and that byte will contain information about which registers are involved, if any. The opcode byte might be followed by, the next instruction. In other words, it might be just a single byte by itself, or it might be a 2-byte instruction, in which case the opcode is followed by an immediate 8-bit value. For example, the move immediate instruction will move an 8-bit value into a register, so the second byte of the instruction would be the 8-bit binary value that gets moved into the register. In the case of 3-byte instructions, the opcode byte is followed by a 16-bit value, and the first byte here, the second byte of the instruction, is the most significant byte of the 16 bits, and then the final third byte of the instruction is the least significant byte of the instruction. So we can break the instructions into a number of different categories, and let's go ahead and take a look at those next. As I said, we've got about 155 different instructions, but before we talk about them individually, let's look at them in these general groups. So we have a small number of different groups of instructions. And the first one is probably the easiest to understand. This is the set of move instructions. So the first column here shows the opcode, or suggests it anyway, and the second and third columns here show the second and third bytes of the instruction, if any. The move instruction is just a single byte instruction, so there is no second or third byte. And what does the move instruction do? Well, it copies an 8-bit value from a source register to a destination register. The source and the destination could be any one of the 8-bit registers. And so there are a number of fields in the opcode byte that indicate which registers are involved as the source and the destination. And because of the variability in the opcode, there are actually 64 different opcode values that are used for the move instruction. So in some sense, we can say we have 64 different move instructions, but I think it's easier to think of all of them as just instances of the move instruction, where you have different source and destination registers. The next instruction that we want to look at is the move immediate instruction. And this is a 2-byte instruction. The second byte is an immediate 8-bit value, and that value will be moved into one of the 8-bit registers. So over on the far right, I'm suggesting what the instructions do, and I'm also hinting at what the assembly syntax is. So we can just code something that looks like this with an equal sign to move a value into a register, and the appropriate opcode byte and second byte will be assembled. Since there are 8 possible destination registers, there are actually 8 different move immediate instructions. Now there are 16 different ALU instructions, and these are all slightly different. They do different things like logical operations, and, or, and arithmetic operations like add and subtract and so on. And so they have a number of different syntaxes. And we'll get into these different ALU instructions in a second. But there are 16 different ALU instructions. They all modify the A register, which is also called the accumulator register. And all of the ALU instructions are a single byte in length. There is no second or third byte. There is a compare instruction. Again, it's a single byte instruction, and it compares the A and B registers, setting the condition codes so that after that we can do a conditional branch, which I'll get to in a second. Then we have the load and store instructions. Load is used to move a byte from the memory, from the RAM memory in particular, into one of the 8 registers. So there are actually 8 opcodes associated with the load instruction. This is a 3-byte instruction, so the opcode is followed by a 16-bit value. And that 16-bit value is the absolute address, that is the location in memory from which to get an 8-bit value, which is then placed into the register. In the assembly code, we use brackets, okay, to show that we are going to memory. So any of the instructions that go to memory use the brackets. The store instruction is similar. It moves an 8-bit value from a register into the memory. And so it's followed also by a 16-bit value, which is the address into which we will be moving the byte of data. Then we have a load M and a store M instruction. These are also 3-byte instructions, so they're followed by a 16-bit value. These will move 1 byte from memory into the accumulator register, in the case of the load M, or from the accumulator into memory, in the case of the store M instruction. What address is used? Well, we go to the M register. Remember, that's one of the 16-bit registers. It's actually made of the M1 and M2 registers. And we get a value from that, and we add it to this immediate 16-bit value that's part of the instruction. And that gives us the final address. Now, if the immediate value here is 0, then M just is basically a pointer. It can contain any address, and that would indicate which memory location we want to retrieve data from or store data into. Or it could be that the immediate value is the address of something in memory, the absolute address of, say, an array or table, and M contains an index into that. And so we add those two together to get an actual value. Then we have the load code instruction, and that will go into the flash memory. So in the assembly code, we write this word code along with the brackets, and that sort of an indication that we are going to the flash memory. And the address comes from the XY register. And we move a byte, we retrieve a byte from the flash memory and place it into the accumulator register. Obviously, there's no store into the flash memory because the flash memory is fixed, read-only memory. Next, we have the add 16 instruction, and there are 8 different variations because there are some options as to what the destination can be and what the source is going to be. But essentially, this is a 16-bit addition instruction. So it's a 3-byte instruction, and it's followed by a 16-bit immediate value. And that immediate value is added to the contents of one of these registers. And so in the assembly, there's some options. These brackets here are part of the syntax and notation that I'm using, and they're not indicating that we're going to memory. This add 16 does not reference memory at all. But what it does is it's going to do the addition and then store the result in either the M or the XY register. So these are both 16-bit registers. And the thing that's going to be stored is computed as the result of adding this immediate value with either the previous contents of the M register or the XY register or the A register or with just 0. So in the case of the A register, which is only 8 bits, it is 0 extended to 16 bits. So it's an unsigned number, essentially. And in the case of 0, it just means we're going to load the immediate value itself without adding it to anything into the destination register, either M or XY. So this thing can be used in a number of ways. For example, if both the source and the destination are M, we can use it just basically to increment one of the 16-bit registers. Or if the source is 0 here, perhaps we're using it to load an immediate value into one of the registers. Or we can use it to move a value, a 16-bit value, from one register to another. The addition here is does not affect the condition codes, so there's that. Then we have the conditional branch instructions. There are 16 of these. There are 16 different conditions that can be tested. And so this is a 3-byte instruction. The second and third bytes provide an address, a 16-bit absolute value, which is used as a target address. And the condition code, which is part of the opcode byte, will be tested. And if that condition is true, then we'll take the jump and jump to the particular address that's given in the second and third bytes. And of course, if the condition is not met, then execution will continue directly after the branch instruction. One of the conditions is always true, so an unconditional goto, or just a jump instruction, if you will, is a special case of the conditional branch instruction. Sometimes it's important to compute a target address and then jump to it. This might be useful in implementing a switch statement, for example. Or maybe if you're doing object-oriented programming and you want to implement dynamic dispatching, you would need to jump indirectly. So in the case of the go to XY instruction, the address that we're going to jump to is contained in the 16-bit XY register. And so what this will do essentially is copy the value that's in the XY register to the program counter. We have several stack instructions. We have a push, a pop, a call, and return instruction here. And we need to load the stack pointer before we use these. So we have a special instruction for that called load stack pointer. And it's followed by a 16-bit value. That's an absolute address. And that address will be moved into the stack pointer. So once we've initialized the stack pointer, we can push things onto the stack and pop things. And we can also call functions and return from functions. The push instruction has 8 variations because you can push any one of the 8-bit registers. And likewise, you can pop from the stack by using the pop instruction. Of course, it's important to call subfunctions or subroutines from time to time, and whenever we want to call a function, we use the call instruction, which is a 3-byte instruction. The immediate 16-bit value is the absolute address, and it would be coded in assembly language, just like this. That will take the return address, that is the address of the instruction following the call instruction, and it will push it onto the stack. Later, when the function completes, it will execute a return instruction, and the return instruction is going to pop a value off of the stack. That would be the return address that we pushed earlier, and then it would jump back to that and continue execution after the call instruction. So the call and the return instructions are very useful for implementing functions. We also can do input and output to the outer world from the core. And in the case of the EveCore architecture, we have a space of up to 256 so-called I/O registers. And we have an in instruction, which is used for getting data from a peripheral device, and the out instruction, which is used for sending data to the peripheral device. And so in the case of the in instruction, which is coded like this, we have to name which of these 256 registers we're interested in, and that is in the immediate 8-bit value that follows the opcode. So this is a 2-byte instruction here. And a value will be fetched from one of these registers and moved into the accumulator register. And for the out instruction, we copy an 8-bit value from the A register to one of the I/O registers. And how exactly these I/O registers are defined is somewhat implementation specific, and we're not going to be talking about that in this video because it can vary. But we'll see in our example program that one of the I/O registers is used for the UART device, and we use in to get a byte from a device, and we use the out instruction to send a byte to the UART and to print the character on some screen somewhere. And finally, we have a no-op instruction. It's just a 1-byte opcode. There's no second or third byte, and that does nothing. That it can be useful for implementing the FPGA and watching exactly what happens. It might also be used in programs that have some specific timing requirements where you want to introduce a specific delay. But other than that, you don't use the no-op instruction too often. Now let's take a look at an example program for the EveCore architecture. Here I'm showing the source code file. Assembly code files end with a .s extension. Every line is an instruction. Okay, so here we see a move into the XY register, and here we see an unconditional jump instruction, and so on. Some lines will be comments, as you can see, and some lines will contain a label. Labels are always followed by a colon, so we can see that main, loop, and message are labels, and these are referred to in instructions. Here we're calling something. The print label is shown a little bit further down here, and here we see a reference to loop. Here's a reference to main and a reference to the message label. So every instruction occurs on a single line, and there is no semicolon, so this is a little bit different than other programming languages. We've also got something called assembler directives, and you can tell those because they begin with a period or a dot. So we see 3 of those in this program: .flash, .string, and at the end we see a .equ or equate. And so let's go through this thing line by line and see what it does. The comments over here suggest exactly what it does. Basically, it's echoing 1 byte. It's reading 1 byte from the UART and then sending it right back. It's also watching for the Q character. It begins by printing a greeting, and if the Q character is typed, it loops back and prints the greeting again, and then goes back into this loop, which is echoing bytes. So let's go through this in a little bit more detail. On entry, we begin executing at the beginning of flash. So the flash directive tells the assembler that anything that follows will go into the flash memory. There's also a .ram directive. That's not shown in this example, but it would be used to lay out the addresses in the RAM memory. So we could say where our variables will go. But we're not using the RAM in this example, except we are using the stack. We'll be using the stack when we call the print function. And so we need to initialize the stack pointer. So our first instruction is the load SP instruction, which moves the value 0 into the stack pointer register. In this architecture, like in many computers, the stack grows down from high or larger memory addresses toward low memory, smaller addresses. And so we want the first thing that we store into the stack to go into the very last byte of memory. The stack will pre-decrement before it stores, so the appropriate initialization for the stack pointer is 0. And then we can begin using the stack. And by the way, if we don't have a full 64K bytes of RAM, then the stack pointer will have extra bits, and the upper bits that are not needed will be ignored. So in any case, this initialization to 0 is appropriate, regardless of how much RAM we have. This means that the stack will start in the highest address of memory and grow downward. Okay, the first thing we do is print the greeting, which is shown by the comment over here, and we will call this print function. Now, just to look ahead, the print function will be passed a pointer in the XY register to a null terminated string in the flash memory, and it will then print it and return. So here we're defining our string. Okay, we've got some characters, echo program, new line, please type, and it ends with a null byte. And this label message is associated with this string, or more precisely, it labels the address, or it's associated with the address of the very first byte in that string. So here, when we load XY with this constant value, we're moving the address of the string into a register. And then we call the print function, and it will print out the greeting, and then it will return. And at that point, we go into a loop. Okay, here we see an unconditional branch to loop, and we just keep repeating, and every iteration of the loop will read a character using an in instruction, and it will echo that character using an out instruction. So the in instruction requires an 8-bit immediate value, and that's given symbolically here. And the out instruction also requires an 8-bit value. These two values are the addresses of the I/O registers, the address of the register that's used for the in is given by this symbol, and the register that's used for the out command is given by that symbol. Now, if we go down to the bottom of the file, we can see an example of the EQU, or equate, a directive. And what that is it always has a label on the same line. And over here in the operand area, we see just a 0. But in general, this can be any arbitrary expression. The expression must be evaluatable by the assembler at assembly time. So this is not a variable stored in memory. This is a symbol that is defined by this particular equate. And it's a little bit similar to, say, a # define in the C programming language. We're using the same I/O register number for both the transmit and receive, and it's a pretty simple expression here, simply the number 0. But in general, it could involve lots of numbers and some operators such as add, subtract, and, or, and the shift operators, and so on. Anything that can be evaluated at assembly time. It can include other symbols as well as constant values, and it can include decimal and hexadecimal both. But in any case, we have equated these two symbols. This might be useful if we ever intend to port this program and other registers will be used. It's also useful in documenting the code. So let's go back up here to the top, and we see that we are reading a character from the UART, placing it into the A register. And the next instruction on the next line, remember, in assembly code, every instruction is on a line by itself. There are no semicolons, and the end of line character is significant. On the very next line, it is copied to the output with the out instruction. After that, we execute a move immediate instruction, which moves into the B register the ASCII code for the Q character. After that, we will be comparing that Q to whatever was copied. It's still in the A register. So the move I will not set the condition codes, but the compare instruction will set the condition codes. And then we test the condition codes to see whether those two values were equal. So here we see a conditional branch, and the condition we're using is just equal. Compare essentially subtracts B from A, and if the result is 0, the 0 flag would be set. So this equal condition is basically testing to see whether the 0 flag is set. That is, whether A minus B is 0, or to put it another way, whether the values in the A and the B registers are equal. And if so, we go to main and then print our message again. Otherwise, we continue executing. And here we see another example of the branch instruction, but this is an unconditional branch. And so in the assembly code, we just specify it as a goto, and that causes us to loop back up here. So we print the message, and then we echo for a while until a Q is hit, and then we repeat. Now let's look at the print function down here at the bottom of this source file. And we see some comments. Commenting is critical. By the way, I've commented this code up here in a style that I recommend. You can see that every line is commented, and in some cases I have a blank comment, like right here. That is used to indicate that this comment on the previous line just applies. So echoing 1 byte, that really is these two instructions here. And this comment, if Q, then go to main, applies to these 3 instructions here. And so that's a style that allows you to just basically look at the comments and find out what the code does. Now, in a small program like this little demo program, that's probably not too important. But when you're dealing with large assembly language programs, commenting becomes absolutely critical because it's difficult to read this code. By the way, this assembly code for the EveCore is a little bit different than traditional assembly languages. It's designed to be a little bit more human readable, and so this is something I'm introducing that I hope makes sense and makes assembly code a little bit more accessible to first-time assembly language programmers. So continuing with the print function, we see that it's passed a pointer to the string in x, y, and a critical aspect of functions is to document what the arguments are, and we're doing that here. And if there's a returned value, what register is it returned in? It's also very critical to document which registers are modified. So in a microcontroller, we don't really have any conventions as to which registers are modified by functions and which are not. So it's important to document. And in this particular example, we are modifying, or we can say trashing or destroying or using registers A, B, and XY will be changed. So we have a line that tells that to anybody that wants to read this code. So here we can see an unconditional branch to the print label. And so we have a loop. And what is that loop doing? Well, it's fetching something from the flash memory with this load code instruction. This uses the address in XY and grabs a byte and puts it into the accumulator register. And then here, with this out instruction, you can see we're copying it to the UART, and then we're looping back. So this runs through the string, getting bytes and sending them to the UART. After we get the byte, we increment our pointer. So here we're using an add 16 instruction to perform a 16-bit addition to the XY register. And then we're testing to see whether we've gotten to the null character at the end of the string. So we have a compare instruction. First we load B with 0, and then we ask, does the value in A equal that 0? And if so, we jump to print exit, which then executes a return statement. But if not, we go ahead and copy that byte to the output and then loop back. So hopefully this example program shows you what EveCore assembly code looks like. Writing assembly code requires practice and experience. So the way to begin is to look at programs and give it a go. So this is a program you might want to type in and execute after you watch the other videos and implement an EveCore processor on your own personal FPGA board. So we'd like to load this example program into the flash memory and execute it. And before we do that, we have to assemble it. The assembler program will take the source code and it will figure out which bytes are required and where they're going to be placed in the flash memory. So here we see a command line that invokes the assembler, and we provide the name of the source file as echo.s, and we are producing an output which we'll call echo.text. The -L option means produce a listing, or produce the output in listing format, and that's very human readable, and we're showing it down below. So the next thing we do here is just use the more command to display what's in that file. So let's go ahead and take a look at the listing output that's produced for this sample program, because that will tell us what's going into flash memory. On the right hand side, the assembler just repeats the source code with line numbers. And on the left hand side, we see the bytes here that go into memory. On the left hand column, we see the addresses into which those bytes are placed. And so, for example, the first instruction is the instruction that initializes the stack pointer register. That's a 3-byte instruction. And so we see the opcode here, C0, and the immediate value is just hex 0000, and so the second and third bytes are there. So that takes the first 3 bytes, and that brings us up to address 3, and the next instruction is loading the XY register with some constant, and that is the address of the message string. And that's down here. And it turns out that the assembler will place that string into memory starting at address hex 16. So you can see that the code produced for this instruction substitutes hex 0016 for this symbolic thing that we used in the example source code program. So here we see the opcode and the 16-bit immediate value. And we go on like that. The next thing we do is call print. And the assembler puts print into memory somewhere. And apparently it put it into address 0033. And if we scroll down here, we can see that, yes, in fact, the print function begins at address hex 33. So let's go back up here. And we see the instructions going in, just as we explained. And here's the move I instruction that moves the character Q into register B. The ASCII code for a Q character turns out to be hex 71, so that's the immediate 8-bit value in this instruction. And here we see the compare, here we see the conditional branch, and it goes to the label main. Well, that's at the very beginning of flash memory at location 0. And then the unconditional jump is to address loop, and that went into location 0009. And so that's why we see the assembler has placed those bytes right here. The message string has a number of bytes, and starting with the new line character, which is hex A, and going on and on and on, and finally ending with the null byte. And then if we scroll down a little bit more, we see that the print function goes into location 0033, and we have a number of instructions, and that is shown here. And finally we end with the return instruction, which is placed into this address, hex 42. So we went from hex 00 to hex 42, that's hex 43. So down here the assembler tells us that we have a total of 67 bytes going into the flash, which is hex 43, exactly what we'd expect. We also see that the assembler produces a line for the EQU assembler directive. Here we could have any arbitrary expression involving other symbols like print or message or whatever, or UART receive. But in this case, we just had a simple value, and it shows the final value of that expression over here. We didn't use the RAM. Well, actually, at execution time, the stack would be in the upper part of RAM, but we didn't actually have any data placed into RAM locations. The assembler is capable of placing bytes into the flash memory, as we see here, and it is also capable of dealing with the RAM. We can define certain locations to hold bytes or half words, that is 16-bit values, or 32-bit values, and we can skip over bytes. So we can use symbolic labels for variables that will be placed into the RAM, but we don't see that going on in this example. So the assembler tells us that as far as it knows, we have not used the RAM at all. So that's the listing output from the assembler. We have another form of output that is actually used to load the ROM or load the flash, but this is the human readable form of what the assembler is doing to our source code program. Now let's go ahead and run our simple example program and see what happens. First, we need to assemble it. I've opened up a command line shell window here, and the command that we need is this one right here. This invokes the assembler that I wrote, and the input is a file that contains our source code assembly language. And the output file is specified here, romdata.hex. So we can go ahead and run that command. And if there had been errors in our source, they would have been printed here, but there were none. So now let's take a look at what is in this romdata file. And we see that it's just a bunch of bytes that are not particularly meaningful to us humans. These are the bytes that will be used when we run the Lattice IceCube 2 software to build our FPGA. It will go to this file and collect these bytes and use them to initialize the block RAM memory. But in order to see exactly what the assembler is doing, we can also use this assembler to produce something that's in the so-called listing format. So with this command, again invoking the assembler on the same input file, but now using the -L for listing. And we're also going to specify a different output file. When we run this, it produces a file. And if we take a look at what's in that file, we see this. And what do we see? Well, on the left-hand side, the assembler is printing out the addresses. And then here, it's showing the bytes that are going into those addresses. So we see, for example, the call instruction right here went into address 6, and it had an opcode of C3 and an immediate address of 0033. And we see that other instructions, for example, take only 1 or 2 bytes. Now, if we scroll down to, say, 0033, okay, let me go back up a little bit here. We see that at 0033 is the first instruction of this print subroutine. Also, I should note, at the bottom of this file, the listing includes information about how many bytes it actually produced. Okay, now I've already flashed the FPGA and we are ready to run it. I've got a little terminal emulator program, and that's shown right here. This program is called CoolTerm, and it works both on the Mac and on Windows. On Windows, a lot of people also like to use TerraTerm, which is a similar kind of terminal emulator program. And basically, what we're going to do is connect this program to the FPGA, and it will communicate over the USB cable. So when our code prints to the UART, it will go through the USB cable, and the characters will be displayed in this window here. So now I'm going to go ahead and reset the FPGA by pressing these left 2 buttons here. And that raises the reset line and causes the reset. And we see that it prints out our greeting message. And now I can type, for example, A, B, C, and it echoes just as we would expect. And then when I hit the Q character, like this, it just loops back and prints the greeting message again. And so it looks like our program works just as we expect it to. Next, let's take a look at how the move instruction is encoded. All instructions are encoded with an 8-bit opcode, which we see right here for the move instruction. In particular, we see 2 fields, one for the destination register and one for the source register, and these are encoded with the obvious 3-bit encodings for the various 8-bit registers. This particular instruction takes 64 of the available opcodes, or 1/4 of all available 8-bit patterns. The other instructions are encoded in various ways. Now, let's take a look at the ALU instructions. There are 16 different ALU instructions, and you can see that the opcode has a 4-bit function code field. So down below we're listing all 16 different instructions as determined by the function code field. So let's take a look at these. We've got logical operations, we've got arithmetic operations, and some shift operations. In the left-hand column, we're showing the function code field, but in the middle column, we're showing the assembly code. This is exactly how you would specify the instruction in an assembly program. So you'd specify these tokens exactly as they're shown here. This is an 8-bit ALU, so each operation is working on the 8 bits in A and B and placing the result in A. The operands always come from the A and B registers, never from any other registers. So with the first instruction, the AND instruction, this is a bitwise AND, so each of the 8 bits in the A register are ANDed with the corresponding bit in the B register, and the 8-bit result is moved into the A register. The logical OR instruction is shown here, and we have a logical exclusive OR instruction, and this is the logical complement instruction. Here we see the addition instruction, and it's an 8-bit addition. If you want to add 2 numbers that are greater than 8 bits in size, then we have an add with carry instruction that you can use. Here is the 8-bit subtract instruction, and there's also a subtract with borrow in case you want to subtract 2 values that are larger than 8 bits. Here is an arithmetic negation operation, and here's an instruction that will clear the accumulator. We have 4 different shift instructions. All of the shift instructions move the argument by 1 bit position. In the case of the first shift left instruction, we're shifting a 0 in on the right end, and we're shifting the bit out into the carry. All of these 4 instructions will modify the carry bit. The bit that's shifted out, either on the left end or on the right end, will be moved into the carry. With the second shift left, the shift left through carry, we will be shifting in not a 0, but the previous value of the carry flag. With the shift right, we are shifting a 0 in on the most significant end, that is the new sign bit. With the shift right through carry, we will shift in the previous value of the carry flag on the left side. And finally, we have instructions to both increment and decrement the accumulator register. All of the ALU instructions set the condition codes, and the compare instruction also sets the condition flags as well. And after that, you might want to do a conditional branch instruction. So let's take a look at how the branch instructions are encoded. The 8-bit opcode contains a 4-bit condition field, and the various values for the condition field are listed down here, so we can test for various kinds of things. The opcode is always followed by 2 additional bytes, which give a 16-bit address. If the condition is true, that if it's met, then execution will take the jump and will go to the address specified with that 16-bit value, and otherwise we'll continue executing after the branch instruction. So now let's take a look at these various condition codes. In the middle column, we show how they would be specified in an assembly language program. In other words, in the goto instruction, we would use these tokens exactly as shown here to indicate which condition we want to test for. And on this column here, we're showing how the condition code bits are tested to determine whether the condition is met or not. That is, if this stuff is true, then we'll take the branch, and otherwise execution will continue after the branch instruction. So the easiest to understand are the equal and not equal tests. So these simply test the 0 flag. So remember that the compare instruction is like a subtract instruction, and if the 2 arguments are equal, when we subtract them, we would get 0. That would set the 0 flag. And so a test for equality will jump if and only if the 0 flag is set. That is, if the 2 arguments were equal. And the test for not equal is just the opposite. Then let's look at the unsigned tests. So we can compare less than or equal, greater than or equal. And by the way, the assembly code uses tokens that look exactly like this to indicate that this is an unsigned comparison. So it turns out that you can determine whether 2 numbers are less than by looking at the carry flag alone. And less than or equal is just the carry flag or the 0 flag. And the greater than is just the logical opposite of the less than or equal. And we can see that going on here. And finally, the greater than or equal is just the opposite of the less than. So we see that the greater than or equal unsigned test is just looking to see whether the carry flag has been cleared after a subtraction or a compare instruction. We also have signed comparison, and this is a little bit more complex. I'm not going to go into this, but if the 2 arguments, that is the values in A and B, before a compare instruction, are considered to be signed numbers, or if you want to interpret them as signed numbers, you can ask whether one is less than or greater than the other with these particular conditional tests. And this will give the results that we expect for signed comparison. And finally, we have several conditions that can test the sign flag directly and the overflow flag directly. This condition here, 1110, is always true, and so that is used for a simple goto instruction. the branch will always be taken. And the final value is not defined, so we don't want to say anything further about what would happen if that particular bit pattern appeared in some instruction. Now let's see how the conditional branch instruction would be coded in an assembly language program. There are two general forms. In the first one, we specify which condition we're interested in, and the second form is used for the unconditional jump. So here we have three small examples. In the first one, we are comparing registers A and B, and then we see the conditional branch instruction. And this one uses the less than or equal unsigned condition. So if that condition is met, this instruction would jump to some address, which is my label. That's not shown in this example. In the second example, we are decrementing the accumulator register. And if the result is 0, which we're testing for with the branch instruction, then we would jump to a label called it's 0. The final example is just an example of the unconditional branch instruction. Here is the encoding for the add 16 instruction. Remember that the add 16 instruction is followed by 2 additional bytes, which provide a 16-bit value, and that value is added to a source, and the sum is then moved into a destination register. The destination register can be either the XY register or the M register, and that's encoded in the single-bit field here. The immediate value is added to something that's determined by the source field here. These 2 bits indicate whether the immediate value will be added to the contents of the XY register, or the contents of the M register, or the contents of the A register, or perhaps it's not added to anything, in which case the value is simply moved into the destination register. In the case of A, the 8-bit value in A would be 0 extended to 16 bits before the addition. This add 16 instruction doesn't set any of the condition codes. The assembler is pretty flexible in how the programmer can express the add 16 instruction. And up on top we see some various forms that are usable, and down below we see some examples. So for example, we can load the M or XY register with constant values, perhaps expressed as a label or symbolically, or perhaps expressed in hex or decimal, or perhaps as an arithmetic expression of combining these two things. And in these other examples, we see that we can use it to increment the M register, or maybe offset from a particular label with the A register. And finally, we see that we can use this instruction just to copy from one register to the other. Going back to our original chart, we can see that we've covered all of the instructions. We have a register-to-register move. We have an ability to move an immediate into a register. We discussed the 16 ALU instructions, the compare instruction. We talked about the load and store instructions, which take an absolute value as an address. And we talked about the load M and store M instructions, which find the address in the M register and add an offset to it. And in some cases, the offset could very well be 0, in which case we're just using M as an index register. And we have an ability to load from the flash memory using the XY register. And then we have the 16-bit addition instruction, add 16, which is capable of doing several different kinds of things. We talked about the conditional branch instructions. We talked about the indirect jump instruction. We also have an instruction to load the stack pointer, and we have push and pop instructions, and we have a call instruction as well as a corresponding return instruction, and we have the in and out instructions that read from the I/O registers. And finally, we have a no-op instruction. I didn't mention the encoding of that, but it's any instruction where the opcode is all zeros is considered to be a no-op. And so that pretty much wraps up the instruction set architecture of the EveCore. Thanks for watching, and see you in the next video.